Okay, so hello everyone. After a long time, I was busy with my schedule and yeah, so recently I have joined as a PhD scholar in Okinawa Institute of Science and Technology in Japan. So I was preparing for my PhD applications, and so I was doing my research paper, so I didn't do any video. So after a long time, I'm uploading one video. So this video is basically about our my recent work regarding on the clock synchronization. So basically, I'll share my slide which I did in my classwork here. So in the next video, I will explain my research paper which is based on quantum clock synchronization. So this one is the this work is entirely based on neural network and LSTM, basically recurrent neural network basically. So in the next video, I will describe about quantum clock synchronization. This is about clock synchronization, a basic idea about this. So let's move towards the slide. Okay. So I will share my screen here. Let us share my screen. It's the entire screen. Yeah. Okay. Yeah, I think my screen is visible to all of you. I think so. Yeah. Okay. So I am Biswaranjan. Basically, this presentation is about my class presentation about clock synchronization. Um, I'm doing my PhD at Okinawa Institute of Science and Technology, OEST, Japan, and the course instructor is Professor Makoto Yamada. So now let's start. Yeah. So our agenda is the content that we are going to cover is that first we'll describe about what is clock quantum what is not quantum I'm so sorry. Yeah, what is clock synchronization, the basic concept of clock synchronization. What is clock synchronization? All those you need to know, right? Then we'll move towards why do we need clock synchronization. Uh, uh, there we'll see some real life examples um, and some scientific applications. Then we'll move towards our problem statement. What are the basic challenges that people are facing to do clock synchronization, and why we are focusing on this point? What are the challenges we want to solve solve the real life problems by using this model. So then we'll, after looking the problem statement, we will see what is our proposed solution to this problem. We'll see the overview. uh, then we'll see what techniques we are using. First, we'll generate our dataset. I have tried to find some real-time clock synchronization dataset, but I got some research papers, but I mailed them, but they didn't reply to me, so I didn't get any data. So I have generated my synthetic data. We'll see how I have created my data. Then here I have used LSTM and Bi-LSTM. We'll see what is the LSTM and Bi-LSTM. What are these? Then what are the results of this? Then we'll see the future works as usual. Then at last conclusion is there. Yeah, so let's go. So first question is, what is clock synchronization? So basically, clock synchronization by precise definition you can see here. So basically, in a for simplicity, let's take two clocks which are apart from a long distance, um, and you need to sync these two clocks so that they will give you the same reading as much as precisely to the reference clock. So in the same way here, like you can use this definition for multiple clocks which are located in different places, right? So one simple example is, imagine you have two clocks at two atomic clocks, so which are located at one is at Tokyo and another is it is at New York. So due to due to some signal delays, you need to send some signal from one place to another place so that that clock can get the data, and we will tune the clock tick, right? So the signal, sometimes signal will be delayed when it will reach to another place. So because of that, the error will be, I mean, the clock time will be lagged behind, right? So because we have seen the clock, if the clock is synchronized, then we accounted the communication delays, then the drift due to frequency instability, then environmental noise. So, as you know about what is clock synchronization, then we'll see why do we need clock synchronization. Yeah. So, why do we need clock synchronization? So one simple example I can say before this, to going to into the slide. Suppose you went to one ATM to withdraw some amount of money. Then what happened? You took your money and from the ATM. Then you checked your balance. If your clock, the time before withdrawing and after withdrawing are not synchronized, I mean to say, if the clock of the ATM was lagged behind, then it will show the same balance before withdrawal. So you will be happy by looking at your amount, right? Because you didn't your amount is not reduced, but as you are happy, but the case is not so real, because at that day you will be happy, but next time when you will come to the ATM, then you will see that my balance is this, and then you will be in trouble if you forget that you have withdrawn the amount of money. So this is a serious problem, right? Do you understand this? So, other than that real life example, we can see some communication system. The whole communication system is based on quantum synchronization, because because we nowadays we are in 5G network, but later we'll go to a 6G network, which is much faster than the 5G. So data packets, so which are transmitted. means when you are communicating with 5G or 6G or any kind of network system, you need to send some data. If you are using internet, so you need to use some data packets, right? If the data packet are not arriving at a particular point of time which was expected, then data collision will happen, and you will lose your data. Your network stability will be unstable. So whatever network you will use, the network will be slowed down, and the bandwidth, all those things will affected by the timing. Okay. So the next one is GPS system. You might have heard about GPS system, the satellite-based geographical positioning system, which will give you the location, the Google map, all those things are working on based on this. So if your clock, if not your, but if your cell phone's clock is not synchronized with your satellite system, then it will be a major difficulties. It will be it will create a major problem to find out your location. So you can see like 1 microsecond clock error creates 300 meter position error in Earth. Like suppose you are at your home, then if your clocks, if the error is one micro second delay, then it will show 300-meter away from your home. So it's crazy, right? Yeah, so at the end, like the conclusion is synchronization equal to accuracy of navigation. And then next we'll move towards our favorite topic, quantum communication and quantum sensing that I'm working on. Mm, so, as people are crazy about quantum key distribution, that quantum cryptography, security protocols, all those things are completely based on quantum synchronization. Completely based on clocks timings, right? Because your photon will arrive at another point, then he or she will do the measurement, then data analysis. These things are done in order, right? And so if the clock, if the two signals arrived at different time, then up means suppose your clock and Alice and Bob's clocks are not synchronized, so it will your measurement data and his measurement data time is not aligned. So it will give a different analysis. Different ordering to your measurement time, right? So basically, this is a big problem in our advanced technology of quantum cryptography, whatever quantum communication, to quantum teleportation, in every field. So here in conclusion, precise timing equal to preserving quantum correlations. Okay, so next we'll see the distributed sensor networks. In our Internet of Things, where environmental mm, monitoring sensors are timestamp data accurately, then unsynchronized clock implies that incorrect event ordering, which leads to analysis error that I mentioned before, right? So other scientific experiments, like if you are doing an other than physics, like so here I have written about informatory, but you can consider in chemistry some chemical reaction time, and In biology, there are so many things which are based on clocks, right? This will create a major severe problem that so clock drift is equal to experimental noise. Okay. Okay. So now we'll see what are the challenges, right? So Mm, so in our real world, every clock drifts. Basically, no, there is no perfect clock. There is no stable perfect clock in the world. I mean, every physical clock. No physical clock is perfect, as I have written here. So, why these things are happening now? Now you can imagine like why this clock is stripped. So the core mechanism is in your cell phone or whatever clocks are there. Inside that, I mean, for example, in your cell phone, the quartz oscillator is used here. But the problem is environmental noise. What is environmental noise? So the environmental noise is when you keep your phone charging, so it will increase your temperature, right? So because of the temperature, the frequency drift will happen. Then phase drift is the frequency drift is a integration of phase drift. So then phase drift will happen. They will be out of phase, right? Then some random timing fluctuation, which is called a jitter. This thing will happen. So, 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 so we can see there are lots of problems will happen because of these environmental factor. Loss of time alignment will happen, then incorrect event ordering, then communication errors, then quantum coherence loss. Usually the qubits are not so stable if you are not considering the clocks drift and all those. Then you will destroy you will be in trouble because of the decoherence. Then reduced measurement precision, which the clock, as I said before, right? In QKD, those kind of protocols, you will lose your data. I mean, it will you will lose your precision of measurement. Okay, so now we'll see what classical synchronization limits. So there are certain protocols which people are using nowadays, which are called NTP, Network Time Protocol, Precision Time Protocol, PTP, two-way sync. These things are there. But in these protocols, the problems are network delays. The network will, you will get some precision, but this precision is not enough, right? And asymmetric noise. If you are sending one signal from A to B, then it and again and another signal is coming from B to A to B, and B to A is not always the same. That's why it's called asymmetric, sorry. Then temperature evasion, as I have this already explained, right? Temperature, why temperature. Temperature variations will happen. Then unpredictable drift behavior. The behavior sometimes, so we don't know why the reason is. Reason of the clock synchronization. So sometimes some random noise will come into picture. Mm, so, these problems of the classical protocols cannot handle the advanced protocol of quantum cryptography and some advanced techniques in future, like in 6G technology or 7G technology, whatever is there. So we need to see some other methods. So our research problem here our core research problem is, can we predict clock drift accuracy enough to achieve nanosecond level or better synchronization using machine learning, deep learning, advanced techniques? So our core problem is rely on this problem statement. Our core project, basically the project, is rely on this problem statement. Um, so the goal is to will be built, as we don't have any data set, so we'll generate our data set by using physics equations. I mean the temperature, frequency, those, by considering those, we can by using some equations we can create our data set. Then we'll apply some advanced models like LSTM, encoder, decoder, transformer, etc. Then evaluate which techniques is predicting the drift effectively. Then achieve in which technique by I mean how can we modify our precision and for this problem. Okay, let's go to our data generation. So basically in it's not so important, it's based on mathematics, so you can only see that some environmental modeling of temperature. So basically the temperature variation is given as by OU model, Ornstein and Uhlenbeck OU model. So here we have created our data by using this equation. It's not so important, but for your reference, um, I am I'm I have given the slide here. Okay, so we have created our data by using these equations: temperature, frequency, and phase. Okay, okay. So next to go towards our data set. So I did the plot of temperature, frequency, and our phase. As you can see in the plot, that when temperature is stabilized, the frequency is also stabilized, and of course the as phase is a the phase is integral. No phase. Frequency is integration of our phase. The phase. No. The phase is a integral of the frequency. So basically, when frequency and temperature, these things will increase and stabilize, then but the phase will continuously increasing, drifting, right? So the phase error will increase. um, so here we have taken 120,000 data points uh, with the resolution of 0.1 second. Basically, what that means, it means that we are taking the data with 0.1 second. So if we have taken 120,000 data points, I think it's a printing mistake. No, it's correct. So we have taken 120,000 time steps, so it equivalent to 12,000 second, because we are taking mm, yeah, actually, these are time steps, so yeah, it's approximately 12,000 second. Hmm. Okay, so so here we have taken delta phi as a function of time, the phase drift, then delta f, the frequency is of course it's a function of time, the frequency drift. Okay. Then temperature, in as usual in Celsius, which according to OU model, it should be 25 degree Celsius, so that you can see in the plot it is near to 25 degrees Celsius. Okay. Okay. So now we will see about the technique that we have used here. So the LSTM, basically LSTM is under the recurrent neural network. So why we are using recurrent neural network? So basically, recurrent neural network is predicting. It has a short-term memory, so it predicts the second sentence. For example, when you as you are using Gmail or some Grammarly software, so it is embedded with your RNN networks. So when you initially, I mean, when you type, I am from basically I am from India. So I am from India. Then in the next step, I will write I speak. Then it will suggest me that Hindi or something like that. So it is basically, it works like that. So it has a memory as the previous neural network, like artificial neural network. Those neural networks acts as individually. So here recurrent neural network acts the as a time series. So here with RNN also, it doesn't have any long-term memory. So here LSTM introduced the long and short-term memory. LSTM, long short-term memory. Here it is smart idea that people have used here. They have used gate system here. So suppose you are writing one paragraph. So I mean, for example, if you are looking some one movie, and after 30 minutes, you realize that you want to remind a particular scene before 30 minutes what was happened. So it based on long-term memory, right? So you need to remind what was the scene, and of course you don't need to remember the color of the shirt that person was wearing at that time. So you need to know the only remember the context. So here different gates are there. By using these gates, the particular things which we want to use at that time, that gate will smartly choose, I mean, pass the information. So here you can see the cell state. The cell state carries long-term information. Mm, the cell state is the brain of this LSTM. Then forget gate, which decides which information we need to means you need to discard from the cell. A cell is a brain, right? So and input gate, which decides which new information we want to add in our system. Then output get decide what to out, I mean, what should we give output from the cell state. And one forget get, which gives which information we need to discard. I already told you, right? I think so. Okay. So this is the LSTM model. So here we are using Bi-LSTM model. So here I want to explain Bi-LSTM model also. So Bi-LSTM model is nothing but by using a two LSTM models in reverse direction. What do you mean by reverse direction? Okay, so the reverse direction means initially we'll use from 1 to t, I mean from past to current, then in the reverse, then future to past, right? So the as you can see, I have written by accessing both past left and future right. The context for each time step by LSTM captures richer contextual information than a than a unidirectional LSTM, right? Uh, okay. So the structure is forward LSTM processes sequence from t equal to 1 to t, and here t to 1. Then at last we will combine the information. Okay, let's go to the next slide to see what is our sketch diagram. Um, okay, so as we are dealing with clock synchronization, the here we are dealing with a time series of data. So our data is data is relevant to the each time step. So mm, we need to care about the current, the his past data, and of course the future data. So if we are using the given data, that we have a data of temperature changes, frequency drift, then phase noise evolution. So here in Bi-LSTM we have two layers basically. I mean, not layers, but yeah, it's a combination of forward and backward process, right? So first we'll train our data in past input state, and another is reversed, that future, I mean the in the reverse way input state. Mm, then we train our data, then predict, then we'll combine these two, then we'll do the prediction. It's a smart idea, right? Okay. Okay, so we'll go to next slide. Our result. Okay, so by using Bi-LSTM, you can see here I have I only did with the phase drift. Mm, so the result is the Bi-LSTM successfully captured. I mean, it's okay. Captured the temporal trend and slope of the phase evolution. Mm, so so qualitatively, we can see the yeah, our R square metric, which is a metric of accuracy, is given as 0.78. So it's a kind of okay. It's kind of nice result. As you can see, the prediction is quite close to the true value. Yeah. Mm, okay. And at last, our visual analysis of just alignment. We have predicted 10-step horizon. Then small deviation appears due to the internet system noise and long-term accumulation error. Okay. I think it's okay. Not so good, but when you will see the actual because our goal is not to predict the data completely, but we need to find out the precision of the clock synchronization, right? So in next slide we'll see the precision of clock synchronization. Okay, so here in this slide I have given the formula of delta t is given as delta phi by 2 by f naught, and here delta phi is our phase error which will be predicted in mm, from our result. And f naught is the the clock carrier frequency, which differs from clock to clock, and delta t is time error in seconds. So by using root mean square formula, we can find sigma phi is as phi true minus phi predicted, average square of root, because it's root mean square, right? Yeah. Mm, so the final time precision formula is given by sigma t is given by sigma phi divided by mm, 2 phi f naught, and here you can see, as we'll find the sigma phi from our Bi-LSTM technique. So after getting this value, so sigma t is directly I mean, it actually inversely proportional to the frequency of the clock, because here we have predicted sigma phi is equal to 1.5458 into 10 to the power minus 5. So usually f naught is in megahertz. So our prediction will be near to the nanosecond regime. Yeah. So it is a nice result. We are happy with it, but we'll see what are the problems with it. So the key limitations, what limitations are there with this nice result? Even you can go, if you take your frequency somehow better, I mean 10 to the power 4 or 10 to the power 5 scale, then you will get the get femtosecond precision. I mean, not I mean, yeah, I mean picosecond 10 to the power minus 12 and femtosecond 10 to the power minus 15 precision. But the twist is here, the limitation is synthetic dataset. Here we have not done the analysis with our real dataset. This is our synthetic dataset, so we cannot trust this simulation. But then the question is why we did with this. So why we did this? Because we are not in a bad condition, because we have simulated our data with considering the real physics equation. Of course, it is also an approximation, but still, as we are getting this kind of precision, when we will move towards the real data set, will at least we can get nanosecond. I hope so. Yeah. So here also we have considered limited noise modeling, that you remember the phase noise, temperature, these things are there. But we have neglected quantum back action, some vibrational thing. That's lots of noise. But yeah. So for here we have predicted for short prediction horizon only 10 steps, which is also a very bad assumption. Also, no hardware validation, so not validated on experiment. Oh yeah, I already told, right? We have not taken the real experimental data. Okay, then we have assumed that we have only two clocks, but in real world there are multiple clocks, right? So in future work, these are the future works that we can integrate hardware data set. I mean, yeah. And also we need to consider multi-clock networks, then long horizon predictions, then noise robustness include, I mean, in the noise robustness, we will include the vibration, electronic, and the quantum noise resources when we will work on quantum clock synchronization. Mm, okay, and also we can see some hybrid models like which combine Bi-LSTM and Clement filters or quantum estimation theory or something like that. Yeah. Mm, so there are lots of work we can do. I am happy to collaborate if someone wants to do more work on this. Okay, so these are the references that I have used to see in the last link. I have studied how to do coding for the Bi-LSTM and LSTM, all those techniques. Okay, so I'll conclude my um, my presentation here. So if you have any questions, you can comment on this, and if you need my slide, if you need some research papers, if you want to collaborate, you can mail me. I will in the description I will give my email ID so that you can mail or ask directly. Okay, so thank you so much. Okay. Okay. The stop presentation and yeah. Okay. See you. Bye bye. Have a nice future.